Hey everyone, so we began looking at this POGIL in class, and I just wanted to finish this up with you. This is the fractional precipitate particular question. I can't remember what it's called, fractional distillation. Anyway, this is number 24. This is probably where many of you guys left off, so let's dive right in. So you've got the solution of lead nitrate being added dropwise to another solution of sodium iodide. And let's see, it also has some sodium fluoride in there. Ooh, super cool. All right, so the Ksp values for lead iodide and lead 2 fluoride are as follows. And so the first question, part A, write the solubility product constant for the precipitates that are expected to form. So there's actually more than one precipitate occurring. Kind of neat. So you got to kind of refresh your memory if you need to on your solubility rules. But the two, because it gives you the Ksp value, you have lead 2 iodide and lead 2 fluoride being formed at the same time. Well, being, possibly formed at the same time. Anyway, all right, so the first Ksp, let's look at lead fluoride. So lead is a positive 2 ion. So I'm going to go like this, Pb 2 plus. Okay, and the other ion is your fluoride ion. Okay, but check those charges. You're going to have to square your fluoride ion. The other precipitate is going to be the lead iodide. Okay, so we would have to do the lead ion. And the iodide ion is -1, so don't forget to square that. All right, state the initial concentrations of iodide and fluoride. So just look back at the original problem that was given to you. So the initial concentration of the iodide ion is 0.0025 molar. And the initial concentration of your fluoride, so fluoride ion, is also 0.0025 molar. So they both have the initial concentration the same. So then it says, which precipitate will form first as lead 2 nitrate is formed? So which one? Is it going to be lead fluoride or lead iodide? And the answer is very simple. You just look at these Ksp values. Who has the smallest Ksp, the lowest value? So the smaller the Ksp, the less soluble it is, and the more likely it would be to form a precipitate. So lead iodide has a smaller Ksp, so it's going to form first. So I would say PbI2 forms first. And why? Because it has a lower Ksp value, meaning that it's less soluble in water. Okay, part D. What volume of lead 2 nitrate will be required for the first precipitate to form? And it says, assume the total change in solution volume is negligible. So remember how, like, as you add the precipitate, the stuff in the burette, and in this case they're adding lead 2 nitrate. As they add lead 2 nitrate, the overall total volume is changing. Luckily, we get to ignore that change in the volume. So now that we know that lead 2 iodide is going to precipitate out first, let's take a look at the Ksp value. Ksp value was 8.7 times 10 to the -9. All right, we don't know the concentration of the lead required to make that ion, okay? But we do have the initial concentration of iodide. It was 0.0025. So I can stick that in, but just remember, you got to square that. All we have to do is solve for that lead. So pause the video if you need to, just to check your work if you want. It should be 0.0014 molar. Now that is molarity. They wanted to know what the initial, how much volume it would take to require that. So pause, look back at the original question. So what volume of the lead needs to be added? So come back. Did they give you the concentration of the lead? Yes, they sure did. It is 1 molar. Think, we want this dude right here to be able to be created. We need that solution to reach that concentration. Pause the video. Think about this. Do you know what the volume of the original solution was with the sodium iodide and the sodium fluoride? Yep, we got that volume right here. All right, so the solution can be found by doing just a quick little mole-to-mole ratio like dilution. You can go M1V1 is equal to M2V2 if you'd like. So this is how I'm going to solve. 0.0014 molar. The volume of the solution is 1.00 liter. If you want to, you can change that to milliliters. Just make sure that if you use milliliters on one side, you're going to use that on the other side. So this unknown volume, I don't know it, but concentration is 1.00 molar. All right, solve for X. You should get 1.4 milliliters. Final answer. Okay, part E. What volume of lead 2 nitrate will be required for the second precipitate to form? All right, so we need the Ksp for the lead fluoride. That's the compound that's going to form second. So I'm going to take the Ksp of 3.7 times 10 to the negative 8. We don't know how much lead has to be added, right? So this is our unknown. But the initial concentration of the fluoride ion is 0.0025, and just make sure you square it. All right, so we are looking for a lead concentration of 0.0059 molar. Same technique as last time, okay? 0.0059. That solution has 1,000 milliliters in there. Oop, there we go. Don't know the volume, but it is a 1.00 molar. All right, let's hook it up. X should be 5.9 milliliters. Final answer. All right, last part F. It says, when the second precipitate begins to form, what is the concentration of halide ion that remains unprecipitated from the first precipitate? All right, so the first precipitate was lead iodide. Okay, so the Ksp looks like this. 8.7 times 10 to the negative 9, right? Now we know what the concentration of the lead is going to be when that second precipitate forms. So look over here, you see that right there? That's the concentration of the lead when the second precipitate forms. So I'm actually going to use that right here for the concentration of lead, 0.0059 molar. Now we're looking for the concentration of the iodide. So I'm going to stick the I in right here, and just don't forget to square it. All right, let's get this going. Solve for I, 0.0012 molar. Kind of a tricky little question, but it kind of makes sense. When the second precipitate forms, what's going to be the halide ion concentration left over from the first precipitate? And that makes sense. All right, question 25. All right, a 0.85 molar solution of silver nitrate is slowly added to a solution containing some chloride ions and some chromate ions. What is the concentration of chloride ions just as silver chromate begins to precipitate? And they give us a couple Ksps. All right, so my first strategy here is to figure out what the concentration of the silver ion is going to be for the silver chromate. And then once I get that, let's see, hold on. Yeah, so once I get that silver ion concentration, I can plug that into the Ksp for silver chloride so that I can get that chloride ion concentration. All right, kind of a wraparound problem. So the very first thing I'm going to do is I'm going to look at the Ksp of silver chromate first, because it's the first one to precipitate. So let's take a look. So grab the Ksp, 1.12 times 10 to the negative 12. All right, think about your Ksp expression for silver chromate. All right, silver is only a positive 1, so you're going to have to square it because the chromate, this guy is 2 negative, so just make sure you square the silver. All right, so let's solve for the silver ion because the chromate, this guy's initial concentration is 0.018 molar. All right, so solve for silver. Okay, now once you get the silver ion, we can plug that concentration for silver into the Ksp for silver chloride to solve for chlorine. All right, so looking now at silver chloride, Ksp of silver chloride is 1.77 times 10 to the negative 10. And think about how you're going to set up this right here. Okay, it's +1, -1, so that's nice. Plug this value in right here, and then solve for chlorine. The concentration of your chloride ion should be 2.24 times 10 to the negative 5 molar. And then we're done. All right, so now let's take a look at the common ion effect on acid ionization. This is the second POGIL that I gave you guys. So it does say here to proceed to question 1 on the next page. So let's go ahead and do that. Question number 1. Match each of the following descriptions with one of the beakers in Model 1. In each case, assume that the change in volume as the solids are added is minimal. Nice. Okay, so hint. Calculate the molarity of any soluble ions after the solid has dissolved or solution has been mixed. Okay. Cool. All right, let's find this first one. A beaker containing 500 milliliters of 1.0 molar acetic acid. Okay, so here is acetic acid, and hold on, let me double check. They're looking for a container that only contains acetic acid. So, look, this guy's got some acetate ion in there, so does this dude. And this one's actually got a bit of acid in there. Okay, so it didn't say anything about any of the additional stuff, so I'm calling this one beaker 1. All right, let's find another beaker that has 0.25 mole sodium acetate, so that's going to contain the acetate ion in there, and dissolved into blah, 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 1 molar acetic acid. All right, 0.25 molar, all right, let's check it out. 0.25 molar acetic acid. Okay, so hold on. There's this guy hanging out right here. And the only reason why I'm drawing your attention here to this guy is because if you were to take 0.25 moles and stick it into 500 milliliters of solutions dissolved in that solution, think about that. That is not molar. That's not 0.25 molar. That's 0.25 moles in 500 milliliters. So it'd be like taking 0.25 divided by 0.5. If you need to, you can do that on a calculator, but I think you guys might realize that that has to be beaker number 3. All right, so this guy right here must be beaker number 3. All right, the next one contains, let's see, we got some zinc acetate, so it's got the acetate ion, 0.05 dissolved into 500 milliliters of 1 molar. Okay, so again, 0.05 divided by 0.5 should be 0.1. So find something that's got 0.1. Again, hold on, let me double check. Yeah, so 0.1 molar acetate. Okay. Am I doing that wrong? Oh, I forgot. Zinc is positive 2. So zinc is 2+, therefore it's going to take 2 acetate ions to stick on there. Yeah, see the formula right here? 2 acetate ions. Okay. So it's actually this times 2 and then divided by 0.5. Holy crud. So that actually gives you beaker number 2. Okay, let's look at the next one. So a beaker contains this many milliliters of 0.4 molar hydrochloric mix. Well, obviously it's got to be the last beaker, but you may just kind of want to double check yourself. So if that's okay, let's do that. So let's take the 0.40 molar, this is your concentration, times it by 0.250 liters, and that will give you the moles of hydrochloric acid. All right, and then what I would do is I'd do the same thing to this other guy. I'd go 2.00 molar acetic acid, and then multiply that by 0.250 liters to get the moles of acetic acid. And then just realize that both of these moles, whatever you get, you're going to want to divide that by the total volume. So 250 plus 250 is 500. So divide it by 0.500 liters on both of these to get the concentration of both of those guys in solution. So that one has to be beaker number 4. All right, so beaker number 4. All right, let's take a look at the next question here. It says, based on the acid ionization constant, that's new, but I mean, you kind of understand that there's so many different types of constants. Anyway, for acetic acid provided in Model 1, do you expect most of the acid molecules to ionize in any of the 4 beakers? That's a good question. And your answer here should be no. And the reason why is because that Ka is so small. Only a small amount of the acid is actually going to ionize anyway. Okay, so there's the answer for that particular question. All right, let's go to number 3. 3 of the beakers in Model 1 contain a common ion in solution. Which beakers in Model 1 contain a common ion? So you may want to go back and double check, but that's going to be beakers 2, 3, and 4. Next part. Consider the source of the common ion in each of the beakers. Does the common ion come from the weak acid molecules? And if not, explain the source of the common ion. No, the common ion doesn't come from the weak acid. It comes from the salt, from the ionic compound that's being dissolved in the solution. All right, so make sure you understand that the common ion is coming from some other compound, not the acid itself. Okay, question number 4. Predict what will be in beakers 1 and 2 when the systems in those beakers reach equilibrium. Use particulate drawings to communicate your predictions. You may omit water molecules for clarity. Okay, so in beaker number 1, let's double check what you've got in there. All you have is the acid, and is the acid going to ionize very well? No, it's not going to ionize very well. So if I was going to draw beaker number 1 in this container, I would have, mostly unionized acid. So what I'm doing here is I'm drawing like a hydrogen ion with an acetate ion like attached. Okay, so for clarity, I'll go like this. This is the H plus ion, and I'll go like this and say that is the acetate ion. Okay, and maybe we'll have like maybe one of them like somewhere. Oops, sorry. Struggling to color that in. Anyway, maybe we'll have one hydrogen and one acetate ion somewhere in that drawing. There, that's my beaker 1. All right, let's check out beaker number 2. So in beaker number 2, you have to remember that we had some zinc being added. You may want to go back and just double check. Look at this part right here. Okay, in beaker number 2, you've got some zinc acetate that was being added. So we do have a common ion, right? The acetate ion, and it's coming from zinc. Now remember, a common ion is going to reduce the ability of an acid to dissolve. So in beaker number 1, I showed 1, 2, 3, 4 compounds unionized. Maybe over here what I'll do is I'll make 5 unionized compounds. 1, 2, 3, 4, 5. 5 unionized. And the acetate ion is going to increase in quantity just because you do have a common ion from zinc acetate. So over on the left, I only showed 1 acetate ion. Maybe I'm going to just throw in, I don't know, like a few more. So I'm going to go with these darker ones. 1 and 2. Come on, 2. Pen doesn't like to cooperate here. And let's see, I'll throw in a third one like right here. Okay, so there's 3 acetate ions. Now we do need to throw in some zinc because the zinc ion is going to be dissolved in there too. So maybe I'll just change colors here real quick. All right, so there's my zinc. 1, 2, 3. I'll do like 3 of those. Okay. Yeah, so there you go. All right, and this is going to be beaker 2. Okay, the Ka expression is pretty easy. This is acetic acid. So just make sure that the ions are on the top. So you can go H plus or H3O plus, I really don't care. And then over here we'll say CH3COO, boop. And stick the whole acid on the bottom, HCH3COO. There we go. All right, now they want you to fill in the data table that was on the initial page back over here, okay? And then in the next question, they actually want you to do the percent ionization as well. Woohoo, fun times. All right, so let's start with this data table over here, okay? So equilibrium, take a minute, fill this in. All right, so let me show you an example of how to do the percent ionization. So here's the Ksp value, or I'm sorry, Ka. My goodness, I've been so used to doing solubility. So the Ka value is 1.76 times 10 to the negative 5. In this first one right here, look at your products. They are both x, so I'm going to say x squared on the top. And on the bottom, this would be 1.00 minus x. So at this point, we just need to solve for the idea that this, anytime you have like a plus or minus x, kind of like what you've got right here, anytime you see that, pretend like it doesn't even exist. Solve for your x without any plus or minus x in the actual problem. That way it makes the math a lot easier. So at this point, what I would do is I'd actually solve for this x should be equal to about 0.00420 molar. All right, let's keep doing that as we work our way through. So in each of the cases where I solve for x, we can legitimize the ignoring of all of these minus x, plus x's. We can legitimize that because all you have to do is compare your x to the initial concentration of the acid. I don't care about the salt, I care about the acid. All right, because we're dealing with Ka here, not the solubility product constant of the compound, okay? So if you're ever wondering whether or not we can, ignore x, what I would do is, like for this first example right here, what I would do is I would solve for x like I did, and then divide it by the initial concentration of the acid, which is 1.00, and then times it by 100. You just need to make sure that it's less than 5%. So 0.0042 divided by 1, and then times 100. That gives me 0.4%. So yeah, I'm okay with ignoring the plus and minus x's pretty much throughout this entire set. Okay. All right, now for percent ionization, super easy. And I just kind of showed you how to do it. This is the molarity of your H plus ion. You see how like we solve for x and x is the H plus ion. So all you have to do is take that value and divide it by the initial concentration right here of the acid. So divide it by 1.00 and then times 100. And sure enough, on this first one, you'll get a percent ionization of 0.420%. Okay, do that for each of the following. And you can check your work with mine if you would like. All right, so we just answered questions 6 and 7. On question 8, it says, does the presence of a common ion with a weak acid, like acetic acid, increase or decrease the percent ionization? So the presence of a common ion, as you can see, look at this. You had a common ion here, here, and here. Look what happened to the percent ionization. It should decrease. So the presence of a common ion seems to decrease the ability of this acid to ionize. Question number 9 says, according to model 1, as the concentration of the common ion increased, how did the percent ionization of the weak acid change? So you can kind of compare, let's see, if you look at beaker 2 and then beaker 3, in beaker 2 the percent ionization is 0.008, And then in beaker 3, it's 0.003. And so we had an increase in the concentration of the common ion. So when a common ion is present in solution, it's going to decrease the amount of ionization that the weak acid can produce. And there's your evidence. Compare beaker 2 to beaker 3. Number 10. Are the data in Model 1 consistent with Le Chatelier's principle? Oh, yeah, it is. So remember, anytime you push on an equilibrium by either adding a substance or taking it away, the equilibrium is going to shift in either direction. So according to Le Chatelier, as a concentration of an equilibrium species is increased, the reaction should shift in a direction that uses up that species. So in Model 1, as the concentration of your common ion increased, the weak acid's percent ionization decreased. This is totally consistent with Le Chatelier. Question number 11. Consider the 4 beakers below. And it says, rank the beakers in terms of percent ionization of the weak acid from lowest to highest. All right, the weak acid ion constant for hydrofluoric acid is 6.31 times 10 to the negative 4. So the weak acid would have the lowest percent ionization, if you look closely, in beaker 3. I want you to take into consideration that this guy right here, this BaF2, has twice as many ions in common, you see the fluoride ion, than the other solutions. So that common ion is going to be double what the other ones are. All right, now let's see. Beakers 2 and 4 would probably have the next lowest percent ionization, as they also contain a common ion. But you see how they're just 1 and 1 ion? So this guy would be the least. These two are kind of tied, right, for the next best. And then this one right here would be ranked as the highest percent ionization because there's no common ion present at all. Okay, number 12. The acid ionization constant for benzoic acid is as the following. Compare the percent ionization of a 1 molar benzoic acid in water with its percent ionization in a 0.5 molar sodium benzoate solution. All right, so this is kind of like the culmination of everything. Use the previous pages to assist you. Start by doing an ice table for when the common ion is not present, and then do another ice table for when the common ion is present. I am not going to give you guys any work. All I'm going to do is give you the final answer. So the percent ionization for no the percent ionization when there's no common ion present is 0.804%. When the common ion is present, the percent ionization that you should get is 0.0129%. All right, I hope this helps, and guys, make sure you're reviewing. Best of luck.